Next, we'll have from Evans et al. Science Backroom Support for Sustained Lunar Surface Operations.
Great, thanks. Can you hear me okay?
Yes, I can.
Okay, great, thanks. So I'm going to talk about science backroom support for sustained lunar surface operations, and I'm going to be referring back to desert rats analog tests to talk about this. So next slide, please. So the current architecture plans for sustained lunar operations include an Artemis base camp around 2030 that'll have a foundational surface habitat that we call the fish with science outfitting. There'll be mobility for astronauts, both unpressurized and pressurized rovers, and then the capabilities for EVAs. And right now the plans are talking about 30 to 60 day missions for humans with the potential for sustained robotic operations for the rest of the year. So there's lots of opportunity for science team involvement for extended lunar missions. There's going to be crew traverses, sample collection, habitat-based science, robotic traverses, and the potential to collect a whole lot of geological samples, potentially exceeding the return mass. So sample prioritization may be required. So we did tests about 10 years ago, desert rats. We just heard about that from David. And part of the tests between 2010 and 2012 included a habitat demonstration unit that was simulated sustained operations. And so it was a habitat that had science outfitting in it. We had a glove box we called GeoLab that was integrated into the habitat, and I'm going to talk about that. Next slide, please. So a GeoLab, it was fully integrated into the habitat structure that you can see down on the lower left. And it was, we had it integrated, the structure, the power, the network, the avionics, the software, and it was designed to receive samples directly into the glove box from the outside. There were 3 antechambers that cut through the bulkhead of the habitat that went directly into the glove box for sample delivery, and then it was configurable so that we could test different instruments. Next slide, please. I'll talk about this in a little bit more detail before we start talking backroom stuff. So the hardware, it was modeled after the curation glove boxes. It was stainless steel and Lexan. It was designed to be able to withstand positive nitrogen pressure. I mentioned that the sample delivery was through the bulkhead through a series of little airlocks that we called antechambers in the back. On the left-hand side, we had several different instrument ports where we could swap instruments. We see a handheld XRF, that yellow thing on the left-hand side. We had network cameras on either side for situational awareness. We had a pan tilt zoom network camera overhead that the backroom could control for monitoring operations. We had a microscope that was a network microscope for doing detailed analysis of the samples, and we had tools inside the glove box itself, touch screens for data entry, custom software for data entry and tracking. We also tested RFID tracking of samples, and the third year we had a robotic sample manipulator integrated inside the glove box. So that's our hardware. Next slide, please. Whoops. Interesting.
Give me one sec. Let me see if I can find.
So while we're waiting, I can potentially bring up or just talk about without graphics. You know, we tested this. We had our objectives included testing the crew, backroom, and samples on a simulated long duration mission. Does the hardware work? We wanted to evaluate science operations that leverage the human presence with robotic tools. You know, what instruments, what tools provide efficient and meaningful data in advance of sample return. And we wanted to look at the scientific contribution of selective in situ sample characterization. Can we boost the mission science and the real-time planning? Can we provide data with the backroom support for informed decisions about sample return prioritization and potentially identify curation requirements? Next slide, please. Okay, so this is a brief overview of operational concepts. So the bottom half is on the surface, and the top half is Earth-based. There were 2 science teams for desert rats. One of them was what David just talked about, monitoring the traverses, but GeoLab also had a science team. It was a pretty skinny science team. We had someone who was the communicator with the crew, someone who was monitoring all the imagery through the cameras as well as the microscope, and someone who was monitoring the instrument performance and the data that was being collected and recorded. So the EVA science team monitored the EVA and the geology exploration per plan and the collection of the samples. They also called the results after a day, and they selected potential samples for examination. They transmitted that information to the GeoLab science team. The samples were then transferred inside, one at a time for examination by the crew when they were in the habitat. They collected basic descriptive information, analytical information. Here you see a handheld X-ray fluorescence spectra and microscopic imagery. Those data were then assimilated and transferred back to mission planning. Next slide, please. So we had, over the 3 years, we built on our basic operations. The first year, we just wanted to test the basic operations with the crew and with the science team and evaluate the efficacy of sample characterization, the descriptions and the imagery and the analyses, and also really evaluate early science ConOps with the science team. And we had some lessons that we learned. And you can see there's some operations. These are images of the lab being operated. Next slide, please. The second year, we realized that the data integration and the data assimilation from the glove box itself was really critical for interactions, both with the crew and with the science team. So we enhanced the crew software and the interfaces, and we had much better data ingest and data organization and recording. We tried new diagnostic instruments. We included JPL's multispectral microscopic imager for data collection, and we tested voice and text commanded communications. And remember, this was about 10 years ago, so it was before the days of Alexa. So it was a kind of new thing, but it demonstrated the efficacy of voice and voice commanded communications. We also tested the RFID technology. Next slide, please. So the third year, we built and installed with collaboration with the University of Bridgeport of Connecticut through a technology project, a robotic sample manipulator that could translate the entire volume of the glove box, but it also had 6 degrees of freedom. So it enabled sample handling with great precision, the potential for automating parts of the analysis. We also tested communications with the crew with a time delay, 50 seconds one way. So this is where understanding how the 2 teams interact was really, really important. Next slide, please. So our lessons learned over 3 years of operations. Number 1, imagery is key, especially for communicating with the science team. Having all kinds of imagery of different scales to understand what's going on and what the data are is really important. Secondly, automated data entry and data recording and data organization are really important. And then technologies like RFID tagging, but also Alexa-like commanding and potentially automated data integration systems and heads-up displays and different types of realities could be really well applied, especially in the constrained volume of the glove box. We realized that the crew can operate relatively autonomously, but the science team can really leverage a well-trained crew, and they definitely lended value by spontaneous observations and operational innovations in that time. Preliminary sample characterization did provide data that support smart decisions for sample handling and prioritization and feeding back into future exploration plans. And so that exchange between the crew and examination and the science team was really important. And finally, robotic sample handling provided consistent and reproducible sample views and imaging and measurements, and that might be really important in partial gravity, and there are other implications of that as well. And then we had ergonomic lessons learned as well. Next slide, please. So future work. we recognize that building and testing, data integration, and new technology applications that could really provide an immersive and collaborative environment between the science backroom and an astronaut crew for collecting data will be really important for both sample return decisions, but also feeding back for future investigations on the lunar surface. Building and testing additional robotic tools for sample handling within an isolation chamber commanded by the crew or potentially the science team might also be really important. Determining the best suites of instruments and data and the operational concepts to sufficiently characterize samples to help inform future exploration will be important. And finally, again, building on that science, engineering, and operations collaboration is key. So with that, I'd like to thank you very much.
Thank you. Perfect timing.